Okay, so this is the first part of this handout, pictures and graphs, that is for a review session for AP Chemistry. And so I'm going to go through several of the questions that are here. And I know that you had to finish up, you were supposed to finish up all of these exercises on here. So hopefully I'll hit some things that you had some particular questions on. And if I didn't, then you can have that opportunity. Text me, let me know. Or email me and say I still don't understand a few of the questions that are here, and I'll be more than happy to answer you. But let's look at the first one. This particular one is just simply using a spectrum to figure out the average atomic mass. And if you look at the percentages, I've changed the percentages to decimal forms. And then looking at the very top number, your mass number is the only thing that they give you for mass. So use that for your mass of each isotope, and then you're simply just going to multiply all of your numbers. So 0.9092, that's my percent changed to a decimal, times 20 is 18.184. Then I've got the 0.0026 times 21, and that is 0.0546. And the last one is 0.0882 times 22, and I get 1.9404. And then this is a weighted average, so you add them up together. This is not like just taking a normal average where you say, okay, I'm just gonna add them up and divide by 3. You're taking a weighted average. So first number plus my second number plus the 18.184. And that gives us 20.179. And since we're dealing with an atom, that would be an AMUs. All right. Okay, the next question has this little series that maybe you haven't seen before. One of the things that we talk about in pre-AP Chem is talking about the atom, how the atom is made up. And so using light to determine that is, we know that electrons are going to make jumps from one energy level to another. So you had to label this. And so if you look at the amount of energy that you can get electrons to move, notice you're not getting very much energy right here. This is only moving from energy level 4 out. And here you're moving from energy level 3 out, energy level 2 out. And this is moving from energy level 1 out. So you have to think about this. Which one's going to require the most energy in terms of which light would require the most energy? Hopefully you know at this point in your scientific career that UV light is going to be the highest energy. So that would correspond to the Lyman series. Visible light, and you could have looked this up, is the Balmer and the Paskin series. And then infrared light is the least energetic of those 3 forms of light. And so it's going to be over here with the bracket series. And this is the only light that we can see. We can't see in the UV spectrum or the IR spectrum, but electrons are going to be making jumps from deeper and deeper into the nucleus of the atom. So energy level 1 all the way out to, in this one, for the UV spectrum, you're going from energy level 1 to energy level 7. So you can see how much energy it takes in order to make that jump. Okay, you have to justify your reasoning, so give a reason why you've labeled these as such. Would a wavelength of light be longer or shorter for lithium for an N equals 2 to an N equals 1 transition than it would for hydrogen? So we're talking about going from N equals 1 to N equals 2 for both lithium and hydrogen. And here's what you have to think about. Which one is going to require more energy to make it go from N equals 1 out to N equals 2? Because the amount of energy is going to be measured whenever the electron falls back to its ground state. So think this through. Who's got more protons in the nucleus that would be pulling those electrons in? If you think about that, you've got 1 for hydrogen, so you've got an electron that's in energy level 1, and you've got 3 electrons for lithium. And so you're moving one of the electrons from energy level 1 away from those 3 protons in the nucleus versus moving an electron from 1 proton in the nucleus. So which one's going to take more energy to do that? Well, that would be lithium, because you're trying to pull that 1 electron away from 3 protons in the nucleus. So it's going to require more energy for the lithium And why is it going to require more energy? Again, it's a proton to electron ratio. One electron trying to move away from 3 protons versus one electron trying to move away from 1 proton. So it's a bigger difference in how much energy it's going to take. Now, the question wasn't asking about energy. It says, will the wavelength of light be longer or shorter for lithium? So you need to understand the relationship between wavelength and energy. The longer the wavelength, the less energy. So it's actually an inversely proportional relationship. In fact, here's the equation for that. Delta E is equal to lambda, let's see, hang on just a second. It's HC over lambda. Okay, lambda is your wavelength. And so if you look at these two things and where they're located in terms of the equation, if I move this to this side of the equation, I'd be multiplying energy times my wavelength, which means that it's an inversely proportional relationship. As energy goes up, wavelength is going to go down and vice versa. So for lithium, which requires more energy, we would expect that to be a shorter wavelength. Okay, so you might want to write that down and study that just for studying purposes, just to have as FYI information on this part of chemistry. All right, moving on into bonding and IMFs. It says, answer the following questions regarding potential energy curves. One of the things that you might need to understand, since we haven't seen this in a little bit, I'm going to scroll over here and I'm going to pull up this little PhET activity, okay? And so we're looking at attractive versus repulsive forces. And if I turn the forces on so you can see them, notice that as atoms get closer together, they're going to be having attractive and repulsive forces. If they get too close together, the repulsive forces of the electrons to electrons and protons to protons are going to override the attractive forces, and so you have a shoving away, okay? Now, right now, these two atoms are actually bonded, but notice that in the bond, you've got the atoms that are literally moving. Okay, I know I set those in motion, but the maximum place for bonding is going to be right down at the bottom of that curve right here. And if you'll notice, these are gently moving in position, but this is where bonding is going to happen. If I can actually move this up. If I move this out, notice that you've got more repulsive forces than you do attractive forces because you've got the atoms that are too close together. So they do tell us on our graph to do some labeling. It says on one side of the curve, it represents increase of attractive forces, and the other side would represent increase of repulsive forces. So this side of the curve would be repulsive, and this side of the curve would be representing attractive. Okay. Now, this little point right here, that bottom part of the curve, is actually where the bonding is going to take place. That's the minimal potential, that's the lowest potential energy. And if I can get these to stop moving very much, you've got a balance of your repulsive and attractive forces. They're balancing out. So if I move these away from each other, notice that my attractive forces are going to, they don't increase a lot until I get them real close together. But if I get them too close together, the repulsive forces are too large. They're still attractive forces, but notice the purple ones, which are the repulsive forces, are going to overcome the attractive forces. And so if you move those two in too close, they're pushing each other away, and there's a point where you can get them too close, and it pushes, the repulsive forces literally push that atom away, and they're not going to be bonded at all. Okay. If we look at the difference between neon and argon, you can actually see, let me toggle back and forth between that. Looking at the dip, neon is a smaller atom than argon. Okay. There is a lowering of potential energy for a bigger atom. In fact, the closer they get to each other, the more attractive forces you have, the lower the potential energy. So if we look at oxygen, it goes off the screen. You can't even see that. But it's because oxygen has this double bond. And so there are a lot of attractive forces there. But there's also a lot of repulsive forces going on because those two atoms are really, really close to each other. The nuclei are extremely close to each other, but there's a double bond between the oxygen atoms. Okay, so hopefully that explained a little bit about that particular curve. On B, it says label the point on the curve that represents the average bond distance between the two atoms. And so that would be here. Why is the distance called the average bond distance? Hopefully you saw that the atoms are like they're moving back and forth in that bond. And so it's not a static thing. It's something that's a dynamic position. So you've got them moving together as they're in the bond. And then it says draw and label a curve that shows what happened if the bond is a triple bond. Well, hopefully you saw that you're going to end up with a huge dip if you get the atoms really close together with a triple bond. So if I'm drawing that on my curve, I'm going to have, I could literally just dip way down here, okay? Kind of do my little curve like that. That's kind of weird, but anyway, that gives you a little bit of an idea of what we're talking about with the this little graph, okay? So on the next one, we've got label the x-axis. And notice I tell you what's a label. It says label the axis. Potential energy is in kilojoules per mole, and bond length is in picometers. So if I'm looking at energy versus bond length, then my bond length is going to be right here, and it's actually shown there. So I'm going to label it down here. So this would be in bond length. And then I'm looking for, that's in picometers, so PMs. And then over here on this axis, this is potential energy, so PE, potential energy, and it's in kilojoules per mole. Okay, and then you have to label those graphs. So I would say that we've got choices between chlorine, nitrogen, and iodine. Okay, these two graphs are going to be the chlorine and the iodine. Okay, I know this is going to be nitrogen simply because nitrogen has a triple bond between the molecules, or between the atoms rather. And so it's going to have the lowest potential energy. The more multiple bonds you have, the lower the potential energy. The closer the atoms can get to each other, and well, we can look at this the simulation again real quick. Okay, if we compare neon to argon, and make this so you can actually see a difference. Okay, so here's neon, I'm sorry, that's argon, and here's neon. Notice which one has a deeper dip. The argon is going to have a deeper dip, although the distance between the atoms, it may be a little bit larger, okay? So if you look at the distance between the atoms here and versus argon, actually it's a longer distance between argon because it is a bigger atom, but it's got a lower potential energy drop. So let's think about where we are on our periodic table, with these two. We've got chlorine versus iodine. And chlorine is a much smaller atom, so that would be this one, Cl2. Iodine is bigger, I2, and it has to do with the attractive and repulsive forces. And so we're dealing with Coulomb's law here. Force is proportional to Q positive times Q negative over distance squared. Now, even though chlorine is a much, much smaller atom, those two atoms are smaller, they can get closer to each other, okay? So their bond length, if you think about that, their bond length is going to be shorter, if you look here, versus the iodine, who's going to have a much larger bond length, okay? I guess we're really more looking down here because they're bonded down here. But you're looking at charge, like which one is going to have the lower amount of potential energy. Iodine will have the lower amount of potential energy based on the number of protons, 53, versus electrons, 53. Chlorine has 17 versus 17. So you have a much bigger top number in your Coulomb's law for iodine than you do for chlorine. And this is why you're going to get a lower potential energy drop. They're going to be more attracted to each other in terms of like getting that potential energy to drop down more. All right, so E says which requires energy bond formation or bond breaking. Hopefully you don't have to think too hard about that one. Bond breaking, I almost did the wrong thing there. Bond breaking is going to require energy because you take energy to break something, and when you put them together, it releases energy. What is the bond energy in joules for one molecule of nitrogen? So if we think about how much energy we've got going over here, we've got for nitrogen, the bond energy is going to, here's where your maximum potential energy drop is, and I'm going to call that, say, a negative 930. So that's a negative 930 kilojoules per mole of electrons, or I'm sorry, of nitrogen molecules. And so if I'm looking at 1 mole is equal to 6.02 times 10 to the 23rd molecules. Okay, and so that would get rid of moles and get us into molecules. And then it says in joules. So right now this is in kilojoules per mole, which is why it's really important for you to read the axes. And for 1 kilojoule, there are 1,000 joules. So setting up we've got our dimensional analysis set up so that our units cancel out, and then we just need to do the math. So let me put my calculator over here so you guys can see that. And I need to take my negative 930 divided by 6.02 to the 23rd power times 1,000. And I got negative 1.54 times 10 to the negative 18th. And that would be in joules per molecule. All right, pay attention to what it says on your graphs. Read your information and read your units. Okay, so moving on to some past bonding, let's go into intermolecular forces. The graph below shows the effect of changing temperature of the vapor pressure for 2 liquids, and we have ethane, which is shown. Okay, so if you look at that molecule, hopefully you see that there are no lone pairs of electrons on it. Everything seems to be pretty equal. This is a nonpolar molecule. And all nonpolar molecules only have London dispersion forces that are holding the molecules to be attracted to other molecules. And then we have water, okay? And at this point in AP Chem, you should know that water is polar and water has hydrogen bonding, the strongest force of attraction between molecules, the strongest intermolecular force of attraction. It says, explain why vapor pressure increases with increasing temperature. First of all, you need to understand what vapor pressure is. And so if I put my little globe up here, this globe has some air in the top part of it, right? But it also has some water molecules that have been captured because they're changing into a gas constantly and then going back down into the liquid. With those gas particles that are in this globe right above, here, I want you to see it where you can actually see that we're talking about the globe itself, not the little arm, but inside the globe, those gas molecules are putting some pressure on the top of the liquid, and that's called vapor pressure, okay? Whenever we're dealing with, we want to know, why does that increase with increasing temperature? Because you're increasing the number of gas particles are increasing. Number of gas particles are increasing. Okay, so if we look at which one of these lines is going to be water, they ask you to do that in just a second, but let's think this through. Which one is taking longer or more an increase in temperature in order to produce more gas particles? That would be water. So this one is water, and this one is ethane. Okay, and so you had to do that on C and justify your answer using intermolecular forces. So identify the intermolecular forces for each substance. We've already identified the one for ethane, which was London dispersion forces for ethane. And water, we said, has hydrogen bonding, but it also has the other two. Okay, hydrogen bonding is just the strongest. It has London dispersion forces, it has dipole-dipole forces, and it has hydrogen bonding. All right. Sketch down on D. Sorry, I kind of skipped over some stuff. So anything I skip over, I'm assuming that you can go back and do some justification now that you have kind of the basic background information if you needed it. D says sketch the curve you would expect for ethanol, which is shown. What they don't show are the lone pairs on oxygen. Okay, a lot of times the AP test, writers will ask you to finish the structure, and they'll have like the basic structure already put in place, and all you have to do is draw the lines and dots. So this would be an example of where I have to show just lone pairs. And let's think this through. Does this have London dispersion? Yes, it does. It's polar, so it has dipole-dipole. And because it has hydrogen directly attached to oxygen, it also has hydrogen bonding. But is its hydrogen bonding going to be as strong as water's hydrogen bonding? Well, if you think about it, water is completely polar. You've got a partially negative end here, a partially positive end here. But this one, you really don't, you just have a polar end of the molecule. The rest of this molecule is kind of a nonpolar part. So this is your nonpolar, which would really only exhibit London dispersion forces with, say, if you dissolved it in water. This is the only part of the water of the ethanol molecule that's going to exhibit hydrogen bonding. So I would say that this molecule, ethanol, is not as polar as water is, and its hydrogen bonding is going to be weaker. So I would put it in between water and ethane, but actually I'm probably going to lean toward the side of putting it a little bit closer to water because it does exhibit hydrogen bonding. So I'm going to label this one ethanol. Okay. All right, let's move on to the next page. On the next page, we've got some information that talks about explain the general trend in terms of intermolecular forces. So if I look at this graph and I get rid of the anomalies, do you notice that the general trend for this is that they seem to increase as you're going through, what does that say? As you're going across the period, okay? Because this is going to be looking at the period of the periodic table and what happens to boiling point. That's just plotted. So as we move across the period on a periodic table, this first one would be representing period 2. This next one would be period 3. Period 4, period 5, okay, and then they have the different groups that are going this way. So it says explain the general increase in trends in terms of intermolecular forces. So we notice that as we go across, the boiling point actually gets higher, therefore the intermolecular forces would have to get stronger, okay. Then explain the anomaly seen with these 3, and so the anomalies are right here, and why would those have, like, why would you see their boiling points much, much, much higher? And that would be because they all have hydrogen bonding. If you think about, remember that's with, hydrogen has to be bonded with NOF, NO, or F, or FON, either which one you want to say, and those all 3 have hydrogen bonding. It says, why doesn't CH4 follow the same pattern as NH3, H2O, and HF? It's because CH4 does not have hydrogen bonding. In fact, CH4 is nonpolar, and the only type of intermolecular force that it will have will be London dispersion forces. That's it. Okay. Draw a picture showing the solvation or hydration of MgCl2 in water. All right, so first things first is I want to decide which one of these ions is bigger. And so if you look at, if you look at the periodic table, and I can pull a periodic table up here real quickly so that I'm not just talking out of the side of my head. Periodic table. Dynamic periodic table is a good one. Okay, so we're comparing magnesium to chlorine. Okay, so here's magnesium, but magnesium is losing 2 electrons. So it's going to fall back, and it's going to have the same approximate size as neon because it lost 2 electrons. Chlorine is gaining 1 electron, so it has a negative charge, and so it will have the same approximate size as argon. As you go down the periodic table, remember that you've got the snowman effect, so you're comparing neon to argon, okay, and neon versus argon. Neon is smaller, and that was representative of magnesium, the magnesium ion. Argon was bigger, and that was representative of the chloride ion, okay? So when we draw our little particles, I'm going to represent magnesium with the smaller one. I'm going to make it just a pure circle, and it would have a 2 positive charge, and my little bit bigger ion is my chlorine, and it's going to have a negative 1 charge, okay? So I'm going to put them in, just put them as a solid down here at the bottom. So I've got alternating, actually, you know what? I've got 2 chlorines for every 1 magnesium, okay? So for every 1 magnesium, I need to have 2 chlorines drawn in my picture. So I'm going to have to get busy with this. Not sure that I'm doing a good job of it, but anyway, you get the idea here. Okay, so there's my solid. Now, water comes in here, and remember that these are negatives, negative, 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 negative. And whenever water comes in, water's going to come in and pull these away based on the polarity of water. So if I am water, then the positive part of my little water body is going to be attracted to the negative ion, okay? And so right now it looks like I've got all negatives right here on the outside of this, because let's pretend like I've already pulled off the positives. But the negative part of the water molecule is attracted to the positive 2+ charge. And so I would correctly surround my water molecules, looking like little bears, but with their butts to the to the 2+ ion. And if I'm going to draw my chloride ion in here, then I would switch my little water bears, and I'm going to put their ears next to the negative charge. Okay, so that's how to properly draw solvation or hydration of any ionic solute in water. All right, number 2 says draw the lone pairs of electrons in the structure below. So the only thing that doesn't have enough electrons would be this oxygen. So I'm going to put them in here. There we go. They need their lone pairs on. Show the dipole-dipole interactions between water and the glycerol molecule. Make sure you show examples of the hydrogen and oxygen ends of the water. So if we think this through, the hydrogen end of water is going to be attracted to those lone pairs, and the oxygen end of the water would be attracted to that hydrogen part. Okay, so I've got to draw this properly. Whoops, almost messed that up. Let's do that way. Okay, so hydrogen is attracted to that lone pair. Do dotted lines between them. That's not a bond, that's an intermolecular force of attraction. There we go. Okay, I should probably do that up here on those dotted lines showing their forces of attraction. All right. And then number 3 down here, I think the next video is going to take you into the rest of this because I messed up the video this morning while I was going over that with third period. So I'm having to re-record this part for you guys. So I'm putting my lone pairs in on this one. There's also a lone pair of electrons on the nitrogen, and it says you're going to show how water is going to be attracted to here. So again, water, the positive part of water is going to be attracted like this. The negative part of water would be flipped around on the hydrogens, any of the hydrogens. You're going to have the negative end of water. And again, positive to negative. Just like that. Okay, so make sure you orient your water molecules correctly. Hydrogens, remember, are always going to be the positive part. And so they're attracted to the negative end of water. All right, pick up on the next video. If you haven't had a chance, or if I didn't get it edited properly, you want to pick up on the next video at time 41:22. So skip all that part where I'm just apparently talking to the screen and don't actually have the paper showing, and start at 41:22. Hopefully by the time that you are watching this, I will have already edited all of that other stuff out. And so that may not make any sense to you. Just start the video. But if you see me talking on the video because I was not able to edit it properly, then you see me talking and don't see this worksheet, then skip to 41:22. Okay? All right, I hope this helps. Talk to you later, kiddos.